In the previous video lecture, we have talked about the property of a property of a linear least square estimator that is based on this linear regression equation. We have talked about the unbiasedness of beta hat. We have talked about the covariance of beta hat under the assumption that the noise has uniform variance and X is deterministic, which means the entries in X is not random. Okay, so we have a nice result that least square estimate has the blue property. In this lecture, we would like to extend to the case that the regressor matrix is no longer random. Oh, sorry, it's no longer deterministic. So if you can recall, when you apply the least square estimate to fit a dynamical model, most of the time, this is the linear equation that you will get. So think about when you want to fit this autoregressive equation. Okay, this is ARX. Okay, if you put this into a linear least square framework, you will have that yt is going to be what? Yt minus 1, ut minus 1, and then the coefficient ab, right? And then plus et. Okay. You see that the regressor matrix that will be called ht right now contains the measurements of y and u. Okay, so so this is the same as the regressor matrix X we used before. You see that entries of X now is no longer deterministic because what? Because YT, in this equation, YT is a result from both deterministic input U, but also, I forgot one term, sorry. I forgot to include ET in the equation. This is ARX model. You see that YT is also a function of ET, but ET is random. So the whole process of YT is also a random process. So now in this case, we say, your H is random. If you can recall that when we prove the unbiasedness and when we prove the covariance, we exploit the property that this X is deterministic. So we can take it out from the expectation operation. So in this scenario, let's see. I will give you a statement of the results, not the proof. Okay. First of all, when you have these least square linear regression equation, so of course what you do is you're gonna have data from endpoints, right? And then you use those endpoints to estimate the beta. Okay. Now this is like vector y, this is like vector x, beta plus e. Okay. So the least square estimate is what? The least square estimate beta hat is, can someone give me the closed form formula for least square? Kanatat? Kanatat?
I don't remember it.
Kanatat, you must review. Totok, closed form expression of beta hat. Totok. Totok is not here.
I also forgot, Achan.
Look it up. Look it up. Ping.
Yeah, it should be H transpose X inverse. And H, right? I forgot. Y, right?
X transpose Y.
Yeah, Y. Yeah, Y.
Okay, so by now this is fundamental results. I don't think it's important to know the closed form, all right? To know how to formulate the least square and everything. Please review. Okay, so now I'm gonna plug this in. I'm gonna plug X transpose. I'm gonna so X transpose will be H1 transpose, H2 transpose, Hn transpose, right? Multiply with H1, H2 dot 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 Hn. The whole thing inverse, right? Times H1 transpose dot 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 Hn transpose multiply with what? With Yt. This is the expression. And please see all the terms for this multiplication. Okay, what is it, Sitipak? The term that I marked in the bracket.
Is the square matrix with diagonal is hi transpose multiplied with hi.
No, this is not a matrix. So Sitipak,
scalar h1.
Not scalar. I mean everything in the matrix is so this is like how you write matrix partitioned into column. Okay. And on the right hand side, this is like a matrix that you partition into rows. But when you multiply, you can think of this as a vector, right? But you just multiply it in a regular way. Don't just commute the terms. So it's like you have the inner product between two vectors. How do you compute these two guys? So it's gonna be what?
H1 transpose and H1.
And H1, right? And then
H2 transpose H2.
What is the then? What is the operation that when you say then?
Is the มันก็คือตัวต่อไปครับ
คือตัวต่อไป no let me review you have a matrix A1 A2 A3, right? No matter what dimension they are, but it just assume that all the multiplications agree to be multiplied together. What is the results of this multiplication?
A1 B1
A1 B1
plus A2 B2.
Yes, is plus, all right? That is what I'm looking for. That you just multiply it in a regular way. Don't just commute A1 and B1. Okay? This is like inner product of two vectors. And what? Of course, they are not the same as what? If you see a term like this, A1, A2, just two blocks, and then B1 and B2, what is the multiplication, Sitipak?
A is A1 B1, A1 B2 is a matrix.
So yes, it's gonna be a matrix. Yes, we don't know it's 2 by 2, but it's like there are 2 by 2 blocks. Okay, so the 1 block is gonna be 1 block.
A1 B1.
A1 B1. 1 2 block is gonna be
A1 B2.
Yes, all right, and A2 B1, A2 B2. Okay, I hope everyone is by now should be familiar with matrix operations like this. Okay, now this term I just would like to so the term inside the bracket is gonna be summation of H transpose HT. Okay, H transpose H. And this is supposed to be, Napat, can you multiply this guy in the bracket?
H1 transpose Y1 plus H2 transpose Y2 and dot dot dot
Yes.
until
Yes. Yes. So can I write it into the summation of H transpose Y like this?
Yes.
Okay, right. So basically, this is the what? This is the expression in the yellow box, the yellow box that I would like to verify it for you. Why? Okay, the constant 1 over n here is is added, is not added, is being introduced here, and of course it's going to be cancelled by the 1 over n here. It doesn't change the form of beta hat, but 1 over n here is kind of is put there to get the sense that the summation over n terms, and then you normalize by the number of samples. Okay, so when we do this term looks like what? The summation of many terms, the sum, like, and we're gonna think of when n is large, when n is big, you have a lot of data. So this guy is approximated by what? Expectation of H transpose T y T. Okay, and this guy is going to be approximated by expectation of H transpose H. All right, like think of like the approximate, the sample version of expectation. Now, from here, I'm giving you the result, the final result that, okay, the least square estimate beta n hat under some assumptions that we will talk about shortly in the next slide. But under such assumption, your beta hat is consistent. Consistent is a property of an estimator that study the limit of beta hat. This is called P limit. It is a limit in probability that, this is a mistake, sorry. It says that your beta hat will converge to the true parameter in probability. And the definition of convergence in probability is this. Is the probability that your estimator beta hat, the probability that the distance between your estimator and the true parameter that is small, okay, probability that distance is small is going to approach 1 when data samples are sufficiently large. Okay, so your beta hat, of course, is what? This is beta. This is PDF, okay, of your beta hat. Your beta hat is a random variable, as I mentioned all the time. Your beta hat is a function of y, is a function of data. Your data is mostly random because it's corrupted by noise. Your beta hat is random. Every time you generate new data set, you collect a new data set, you get different beta hat all the time. This means the point, this refers to a point estimate. One value beta hat is a point estimate obtained from using one data set. If we take a look at the PDF, all right, distribution, probability density function of beta hat, of course, it's going to look like something, okay. If beta hat is consistent, it means that the probability that your beta hat lies between the true parameter, the probability is the area under the PDF, all right? That probability must be close to 1 when n is big enough, which means when you use more and more data, your PDF is supposed to be concentrated around the true parameter so that it can make the area under the PDF, which is this probability, to be close to 1. Okay, that's the That's the definition of what when we say the p limit. And then we're gonna say that yes, beta hat has that property, consistent. Secondly, your beta hat, all right, the deviation from between beta hat and the true parameter with the scaling with the square root of root n, it is asymptotically Gaussian distributed with the covariance matrix P. And the covariance matrix P, of course, the bigger, I mean, the smaller, the better. But that matrix P can be given by first the covariance sigma x that involve the expectation of H transpose H and cross correlation between U and X that is involve the characterization of, you know, expectation of these guys. Okay. We have these can be approximate again given a data set. So these two are important results, and most of the, I mean, library package command that use Leastsquare, when it returns the value of covariance, it is based on these results when it returns the covariance matrix for you. Okay. The result that I present here in this slide relies on the assumptions. Okay, what that assumptions are? Okay, we take a look at the beta hat minus beta. So this is like a bias term, right? Your estimator minus the true parameter. So if I use the expression on this page, okay, I use the expression on this page. I play with the equation. So you see that the term here multiply with the yellow term here is identity matrix, right? These two guys, when they are multiplied, is identity matrix. So it gives you beta, the term beta. Okay, and the yellow term with the pink term is just beta hat. Okay, so this is just to verify the expression. But now these term on the right hand side can be written by, you can just use the common factor H transpose, right? And then YT minus HT beta. Okay, and then you're going to use the assumption that your YT is from the DGP. YT equal HT beta plus ET. So this term results in ET, the error term. Okay. Now you see that the bias of the estimations depends on the noise and multiply with some gain. Okay, those gains depends on the regressor matrix. Okay. Now, when you see this expression, we can just apply the law of large number, because again, this is the sum, all right, the sum of many terms when you allow n to be big. As I said before, this term can be approximated by expectation of H transpose HT, and this term is actually the approximation of HT transpose ET. Okay, we have the expression that the first term, the pink term, that, you know, supposed to be invertible. Okay, that is the first thing. So the consistency result that we see previously based on the expression of the bias term on this page. So the results requires that the expectation of HT transpose HT is non-singular, so that these inverse exists. Okay, And now we take a look back to what is the regressor matrix. Most of the times, okay, if you fit a linear dynamical system, your h of t will always have some input sequence inside the matrix H, just like we had before. We gave the example before. This is your H, right? So it's this assumption is not hard to satisfy, and you see the relationship that, okay, that's why we require U to be persistently exciting of order n. Think about when U is not is useless, just like impulse, right? So U is going to be 0, 0, 0 most of the time. And in that case, it makes your regressor matrix what ill condition in the sense that the expectation of H transpose H could be singular if U doesn't contain useful information. Okay, that's one requirement. The second requirement is that what happened to, okay, think about this matrix is non-singular, so it's going to be some gain matrix, right? But then on the right hand side, let me ask you one thing. This bias beta hat minus beta, do we want it to be large or small? Toto, can you answer that?
To be small enough.
We want it to be small, but we keep in mind again that this quantity is random because beta hat is random. Okay, so now we have no control on the pink term because all we know is a non-singular matrix. Okay, but if we take a look at the blue term, so if we want the bias beta hat minus beta to be small, so we would want the blue box to be what?
0.
Yeah, but it's not going to be the exact 0 in deterministic sense, Napat, right? That you just answered.
Yes. Almost
We-
0. Onward to 0.
We want the mean to be 0. Again, this term is random, okay? So at least we want the mean to be 0, and that is why we prefer, we put a requirement that the expectation of H transpose E is supposed to be 0. Okay? Because is that term 0 asymptotically, the bias term is has the 0 mean. And that's why the statement here, beta hat minus beta is asymptotically Gaussian distributed with what? With 0 mean. You see the 0 mean here. Because if the mean is non-zero, you're going to have a problem. Your beta hat may not have the same mean as the true parameter. Okay, let's take a look at this term. What do we see when we required HT transpose ET to be 0? So it means that, or think about the example that I just give you for ARX, right? HT is going to be YT minus 1, UT minus 1, right? And you want this expectation with ET to be 0. So it means that what you want is your noise to be uncorrelated with what? YT minus 1. And also uncorrelated with what? With the input signal. Does it always satisfy? Probably not. Again, if I put an example on autoregressive, ARX model, think about when you find the correlation. Okay, think about the pair YT minus 1 and ET. If you look at this equation, your YT is a function of ET, right? So your yt minus 1 is a function of
ET minus 1.
et
T minus 1.
right, okay. If what? If et is not white noise, what happened? If et has is a noise that everyone know that when you have white noise, when you filter the white noise, you have colored noise. For example, what this is the autocorrelation of noise. It means what? It means that RE at time lag 1 is non-zero, right? Non-zero. In such case, I give you, this is some example of color noise, all right? So in such case, in such example, your yt minus 1 and yt, does it have correlation?
Yes.
Yes, right? It's non-zero. Dun, dun, dun. And what? That's going to be problematic because the assumption that you rely here is no longer satisfied. But if ET is white noise, what happened? This is white noise. How does it change the result? Because your yt is a function of et minus 1, right? And if the noise is white noise, so this is going to be a function of et minus 1. The results of the correlation here is
0.
Is 0. Okay, so the assumptions here is fulfilled. So in this result, we just it leads to the question that the term in the blue box is the requirement that that has to be checked whether it's satisfied or not. It's not satisfied in most cases, and usually it depends on the property of noise. If E is white noise, then it's this assumption is satisfied. And you see that that's why in a lot of the analysis we put the white noise assumption because it simplifies the obtainer result. Okay, to conclude this chapter, we have explained the least square method. The least square framework can be applied to the model. It can be applied to the model. Not only that the model is a linear or nonlinear function in X, but the emphasis is that the model is linear in the parameters. You can have a model that is nonlinear in X, right? This is nonlinear in the predictor, but as long as it's linear in the parameter, you can just use the least square framework to estimate the parameter. A least square solution is unique if X is full rank, all right, in terms of statistic, that is called there is no collinearity, that the columns of X must be all independent. Okay. To solve the least square, the method is mature. You can use scientific software package, or you can just you just know how to compute the left inverse of the regressor matrix. The least square matrix, the least square estimate has the blue property under assumption that the noise that corrupted in the data generating process is homoscedastic. It means that the covariance of E is diagonal in a vector form and is diagonal, and the term in the diagonal is constant. Okay, or in other words, the noise from all each samples, these noise, they are IID, and they have a common variance sigma square. Okay. The least square estimate is consistent if the noise is uncorrelated with the regressor matrix, the result that we just previously mentioned here. Okay, and that is all for the least square estimator in this chapter.